My talk is about the readout scheme for resistive chipless wireless sensors. That's the outline of the talk. I start with a short introduction. Then I will describe the problem. Should I stop? Or? Okay. That's the outline again. After an introduction, I will describe shortly or briefly the problem. Then I will show you our approach, show you some experiment we did, and I will summarize with a conclusion. Okay, RFID and wireless sensing are key technologies for future systems if you think of Internet of Things or smart dust. In our work, we address or here on the right side, you can see a typical wireless sensor network architecture. You have sensor nodes and sensors. And in our work, we address sensors and a very specific type of sensor, namely chipless wireless sensors. In contrast to the previous presentation, these sensors have no chip, they have no intelligence, they are not smart at all. Why are we doing this? Because some people think, and we also, that this type of sensors can save money, for example. Here's a quote from David Laverty, who says passive wireless sensors may save BP more than $50 million a year. We also think they may be applicable to regions where no chip-based sensors can work. For example, in harsh environments. Harsh environments, we think environments which are very hot or radioactive, for example, or where sensors are hardly accessible, where you cannot exchange something. You need something very robust, something very, very reliable. For example, for monitoring of concrete quality in a bridge. Today I will talk about a very specific class of this type of sensors. These are the resistive sensors, because to other types of sensors, chipless sensors, they have one drawback, and this is sketched here. This is a classical scheme here on this side. You see the classical scheme of this chipless wireless sensor. You have here the reader on the left side. You have a tag sketched here or represented here with an antenna and here with a circuitry. And this tag stands, for example, that the common scheme of frequency, a certain frequency band, and the tag answers or backscatters a certain pattern. And in this pattern, there can be fixed resonance frequency for an ID of the sensor, and there can be variable resonance frequencies, which represent somehow the sensing information. And most of these sensors that use this scheme are capacitive sensors, and there's simply a resonance circuit. And this resonance circuit shifts this resonance peak in accordance to the measured quantity. Now, if you have a resistive sensor, this is not possible anymore because you cannot basically detune the resonator. It's just that you modulate the amplitude as sketched here. You have the readout pulse and the backscattering. And what happens is that only with a resistive sensor, the amplitude of this peak is modulated. And this may cause this is not nice for the readout, and especially if you have, for example, multipath propagation as sketched here, you will end up with additional problem. What is sketched here is our measurement scenario that's a little bit more real. It's not a real scenario with a lot of metal around, but you can see you have basically multipath from walls or from the desk, from a table. On the low side, you can see actually what happens. You have this readout pulse, then this backscattered signal, and you have a multipath propagation, which itself can shift the frequency of the resonance peak, and you can have static interference from radar clutter, resulting in, for example, in such a pattern. And in my presentation, I will try to give a little bit insight how you can address this problem to read out this type of sensor. Basically, you can say, this problem was solved already in 1964 by Harrington, because he wrote a paper called Theory of Loaded Scatterers, and more or less this chipless sensor is a loaded scatterer. As sketched here, you have the readout again, you have the tag, and the sensor basically is a load impedance. And what Harrington said, quite simple, forget all about the wireless propagation and all this stuff. I describe this with a simple set matrix, and if I do some basic mathematics, I can use this equation to calculate the load impedance. Quite simple, quite nice, basically works. One problem is you have to determine the 4 unknowns. Now you can say from the propagation channel that there's a certain symmetry. This means you have 3 unknowns. This means you need 3 measurements for calibration in order to determine the Z matrix. And quite often these are the open, the load, and the short circuit here for the load are used. In practice, this is not extremely good because this impedance, what you basically measure, the input impedance in the reader, sees only very, very small variations. What you basically see is the input impedance of these antennas. This means the load changes only very slightly with input impedance. This means noise is an issue. Therefore, we try to address this problem more in a physical way, that we try to understand what really happens. That we started with a full electromagnetic simulation, which is sketched here. This is a very dense thing. We also simulate for farther distances, as you will see. You have a reader antenna here, you have a tag antenna here, and the load, meaning the sensor, would be placed here at the foot point of the antenna. We simulate in the beginning no interference, and we simulated the backscattered signal from the reader, and what we saw on the first hand was clear. We saw a drop down in reflected energy by d distance between reader antenna and tag to the power of 4, which follows the radar equation. That's clear. But another interesting thing that was that we to a matched load to the tag antenna, we didn't obtain a minimal signal level or 0. We obtained the red signal, and for the 3 calibration standard, we received different levels. If we change the type of antenna, for example, from this PFA antenna to a patch antenna, the load and the open level even changed. You can explain this, we will see later on, with structural reflections from the antenna. And what is now the interesting thing is that basically the minimum signal level of these 3 reflections for the calibration standard determines the reading range of the reader. Because you have a certain noise level, you have to add a certain signal to noise distance in order to read out this correctly. Here we assume for our case 18 dB, and you see, if you would succeed to only to work with, for example, 2 calibration measurements, you could increase this operating range. And we were thinking about how can you actually do this. Therefore, we made somehow a signal flow level. That's what microwave people like to do, a model. This is sketched here. You insert a reading pulse here. Some part of the reading pulse is reflected by the input reflection of the reader. Another part is impedance matched to a free space wave and propagates to the tag. And what is called here as tag. And a part of this pulse is directly reflected at the tag antenna without coupling into the antenna. That's called structural reflection, SR, from the tag. Another part is impedance matched to the connectors of the tag, as sketched here, and going to the load and travels back, and so on. You can do this with some mathematics, and what we first neglected for this mathematics is that the wave that is reflected from the tag here, and a part of this is again coupled at the not coupled, it's again reflected at the reader antenna from the structural reflection. We neglect this because this is backscattered and circulates here somehow, but the signal level is quite low. And if you do this, you can do some mathematics. You see the 3 contributions, directly the input reflection from the reader antenna. That's the interferer here, for example, and that's the signal basically from the tag, including multipath propagation. And ST is directly the response of the tag. That's a little bit more complicated term. We thought, how can we simplify this term, and do we have some freedom for design? And that the answer is yes. If we design the tag antenna to be impedance matched, this means gamma tag. This reflection coefficient is 0. Practically designing the tag antenna to 50 ohms, gamma tag becomes 0. And then you can rewrite this equation in a simpler form. I forgot something. The first term basically you can determine with an empty measurement. This means you remove the tag, just measure into the room, and you get this first type. And the second thing, this we call SRD. That's the signal at the reader side, but de-embedded without this contribution. When I show later on measurements, I will refer on this term. And the measurement basically we want to measure is this gamma load here, which is given here. And now comes the story that I said, okay, we design the tag antenna in a way that it's matched to 50 ohms. Then we can simplify this in order to get more or less a linear equation. And now if you look at what we basically want to do is to determine gamma load. We can rewrite this, and we will see that we get an expression like in the form like this, and we see there are 2 unknowns. This means in order to determine these two unknowns, we need now two reference measurements. This is not in contradiction to what Harrington did in the beginning, because this is maybe more or less similar as if Harrington would assume Z22 is constant. This means this fits, but now we have somehow physical insight in this stuff. Okay, I mentioned this that in our later on, basically this S0 is the first term we have to calibrate, but nevertheless I will show you this SRD because this is more physics related and you can interpret this. Okay, what we actually did, we built some of these tag antennas, a patch type antenna here, just a conventional microstrip patch, and a PFA type antenna. We inserted temperature dependent SMD resistors here between the top and ground plate and here on the top side, and we built this calibration standard, open, short and load. The short, for example, with a short circuit, the load with a 50 ohm resistor. Okay, and that's the typical setup we use for measurement. You have the reader antenna here, you have, for example, the tag, you will write the distance, and you have reflections from the surrounding. And for the heating of the tag, we use something like a heat gun. This generates a hot air stream and it heats up the tag. To measure the temperature, we use a thermal imager. Okay, that's, for example, a measurement. Or first, we place the tag in opposite to the reader antenna. We made something like an absorbing environment, this meaning placing some absorbers in order to suppress the static interference. And we measured with different loads, and this followed more or less what we simulated. Here you have the frequency, you have the resonance frequency of the patch antenna, and you see depending on the load, you get different signals reflected. As I mentioned, the loads were inserted in the middle of the patch. Now we removed this load and made measurements over the distance between reader and tag antenna from 0.2 to 1.2 meters. And we see this doesn't follow correctly or directly that what we simulated in the beginning, but there were no multipath. There was no multipath environment. This means the difference what you basically see now is something like a multipath environment. But what you also can see that basically just by using two calibration standards, you can increase the operation distance of this tag. We did this also with a PFA antenna. You get similar curves. Here you can see because this slow signal should not be so low. Despite we have these absorbers, we still get some multipath effect. And compared to the patch, that may be also interesting. The open and the short curve are simply interchanged. This means the structural reflection of such a PFA antenna and the tag is completely different. Okay. These are two curves for two positions of the antenna. This is the sketch of the PFA antenna from the reader side. This means you look just on the small side, and this is you look on the broad side. You see you get very different behavior. And this simple curve from the radii equation is not valid anymore. But as a message is, with two calibration measurements, you can still gain some operation range. And in order to prove this concept, we built this temperature sensors. The SMD resistors are soldered here. These are two in parallel. The DC value is somehow different from the value we extracted because these are normal resistors, SMD resistors, and they are not designed for microwave. This means they have high parasitics, and this influences the value a little bit. But basically, what you can see is you can measure reasonable values for the thermal resistance. Okay. This is I will skip this because of time. Very briefly, what you can see here is the signal level independence. The signal level here from the tag antenna independence of the load impedance. This means of the impedance of the resistor. And what you can see is if you choose this correctly, you can also have quite a high signal. This is influenced by some parasitic. This means if you use such a passive sensor, you have to also characterize it in a microwave way in order to understand the parasitics. I will now conclude. I showed you the signal flow analysis of the system with certain assumptions. Two reference measurements are required, and by the right choice of these reference measurements, you can increase the operation range of the system. This right choice depends first on the antenna type because of the structural reflections and on the specific scenario. I showed some experimental group with a PIFA tag antenna, and this method is also applicable to broadband antennas. This was a monofrequent thing, and this is also applicable to broadband antennas. We have a poster for this tomorrow if you want to just pass by. Thank you for your attention.